only for the insulator sphere. Is that right?
Yeah.
Insulator sphere?
Yeah. Okay, the first thing I'm looking at is the E field. I'm just going to be looking at the region between R is less than big R. So I'm looking at the Gaussian in here. Are you guys seeing a connection between the quiz that I gave you yesterday, that hopefully was gift points, but at the same time, there is a connection to what the stuff I'm doing here? I mean, you need to know your formulas for area. You need to know your formulas for volume. I mean, if you don't know those, how are you going to do the physics? It's just not going to happen. So, what's the area going to be for this Gaussian in here? Right. It's going to be E times 4 pi, which R? Little r squared, because it's the Gaussian, little r. And over here, am I enclosing all the water, or in this case charge, sorry? I'm not, right? That's the question about the water. That's where that came from. How am I going to figure out how much of that charge or that water is enclosed? It's volume proportional, right? So Q, I have to multiply it by the small volume, which is the Gaussian, over the whole thing over epsilon naught. So this is going to be E times 4 pi r squared, little r squared, times equals quantity. This is going to be 4/3 pi. This is going to be little r cubed over 4/3 pi big R cubed over epsilon naught. The 4/3 pi's cancel. The r squared cancels 2 of those. And so I have E equals Q over 4 pi epsilon naught big R cubed times little r. Okay, now I want to figure out the change in potential. I'm going to go from some point B to some point A. So that change in potential, delta V, that's going to be equal to negative integral of E dot dr. So this is going to be the potential at A minus the potential at B equals negative. I'm summing this up from B to A of E dot dr. Okay. I'm going to plug in what E is, this dummy variable. I can't wait. So, what is that dummy variable saying to look at? Little r. So, all this stuff here, what is that? Constant.
That's a constant, so I'm going to factor it out. So it becomes negative Q over 4 pi epsilon naught big R cubed integral from B to A of R dr. Okay, this is a really hard question for people who've never been in calculus, so I'm not going to ask them. They're just going to listen from the people who've been in calculus. If I want to get rid of this negative sign, what can I do to the limits of integration? Flip them. So it becomes Q over 4 pi epsilon naught R big R cubed integral from A to B R dr. Okay.
Does that flip it?
Yeah, what it does is, remember when you plug in, you do you put B in, and it's going to be B minus A. Well, I'm switching the order. Basically, what I'm doing is I'm multiplying through by -1 in here. I'm distributing the -1. Okay, so Now, all this fancy symbol here means is do anti-differentiation. So RdR becomes R squared over 2, which some of you guys forgot on the bonus. Okay, so it's going to be Q over 4 pi epsilon naught big R cubed. Little r squared over 2 evaluated from A to B. That becomes over 8 pi epsilon naught R cubed R sub B squared over 2, or excuse me, not over 2, R sub B squared minus R sub A squared. I factored out the half, took 2 times 4, got 8. So if I wanted to figure out, let's say A was really right at the center, let's say B is all the way out at the extreme edge, if I were to figure out how much higher potential it is at the center compared to B at the edge, I would just simply be plugging those in. I'd plug in the radius, which would be, in this case, what? Big R, so it's going to be big R squared in here. And what is RA going to be? 0. So how much bigger, let's say, how much bigger is A than B? Is that okay notation? That would, actually I'm going to put 0 here. 0 to R. How's that? That's even better probably, isn't it? That would be equal to, that's be R squared over R cubed. That's going to be Q over 8 pi epsilon naught R, big R. So the voltage here compared to there, if I put my multimeter on here, it would be that many volts higher than this outside edge. Even though there's no charge there. Since, you know, there's nothing enclosed. I think I'm going to write that over here so I don't forget it. The voltage at the origin compared to R is equal to over 8 pi epsilon naught R over R. Okay? The reason I'm putting this over the edge is because I think I want to graph it to see what it looks like. Don't forget that's also a square function, right? A parabola. Okay, so can I go ahead and go on to the next part? Okay, the next part is when little r is greater than r. Did you try any of these last night to see how you did? You could be doing self-quizzes the entire time when we were doing these. Okay, the next one. So now I have the Gaussian out here. Still start off with this. It's going to be E times 4 pi little r squared is equal to how much charge is enclosed? All of it. Q over epsilon naught. So E field becomes Q over 4 pi epsilon naught r squared. Questions? Okay. So that's my relationship. So I probably should have did this before. Here's R. I'm plotting E versus R. For that first part, you remember that was linear that we just did? And now it's inverse square relationship. R squared. Okay. Now I'm going to plug it in here. I'm going to go from figure out the voltage at C compared to D. before I start doing the computation, which one's going to be a higher potential? C, only because what's the charge on this thing? Look at your picture, I didn't draw it up here. It's positive. If it would have been negative, which one would be at the higher potential? D, right? Does that make sense? Fine, okay. So going from, let's see, the voltage at C compared to D. So, this delta variable says to look at only what? Little r. So I can factor out Q over 4 pi epsilon naught, integrating from D to C, 1 over r squared, dr. Another way to write this, 1 over r squared, I think you guys would be best served to start doing this based on how some of you guys did, especially calculus people, on the, I forgot the negative, on the bonus. I was thinking that calculus people would get all the bonus. That didn't happen. So you might want to start doing that. So this means to anti-differentiate that. So when I anti-differentiate that, what would that become? Say louder, what? R to the -1 over what? -1. I have a negative here and a negative there. What do they do one another? They cancel. And now I can go ahead and rewrite it. What's R to the -1? That's really 1 over R, right? Now I'm evaluating between D and C. So this would be equal to Q over 4 pi epsilon naught 1 over R sub C minus 1 over R sub D. Any questions what I got over there? Okay, let's take this to the extreme. Let's put C right at the surface. And let's put D way out in infinity. What is 1 over infinity going to be? 0, right? And what is R sub C going to be if it's right at the surface? R. Just R, right? So therefore, right here at this surface right here, the change in potential at R compared to infinity. This is really bad notation, but I'm hoping it makes sense. Probably what they would just simply say in a book, they'd probably just say the potential is R. It's assumed that you're compared to infinity. I'm doing this for now. Okay, so what would that be then? It would be Q over 4 pi epsilon naught big R. Q over 4 pi epsilon naught big R. So let's really quickly look at what the potential versus R graph looks like. Again, I want to draw in R here. Okay, outside, we just found it was what kind of relationship? What kind of relationship? Inverse. So it's inverse. Okay, so that's proportional to 1 over R, right? The derivative of this gives me that. Actually, the negative derivative of that gives me. Okay, what about inside? I erased it already, but look back at your notes. What was the relationship? Is what, right? It was a parabola. So what? Is a parabola like that? No. The other way, right? Like that. So what is the potential right at that point right there? Q over 4 pi epsilon naught R. That's right there.
what is the delta V right here? Going from here up to here, what is the delta V? That's easy, what is it?
8 pi epsilon.
Q over 8 pi epsilon naught R. So therefore, how do I figure out the potential there compared to infinity? I have to add them together, okay? I need a common denominator, that would be 8, so 8 pi epsilon naught R over 2Q on top. Did I do that right? Okay, so what's it going to be up there? 3Q over 8 pi epsilon naught R. That make sense? So if I really want to figure out what this is, where do I have to start at? I have to start out there at infinity. You know, I'm going to work my way inward. I mean, I can figure out all my delta V's like I did just a second ago. That's fine. Realize that's not my answer. If I would have said Q over 8 pi epsilon naught R, that's not right.
Did you say you added those?
Yeah, I just simply added because I found my delta V here, and really this, my delta V here out to infinity. That's where we'll go with that. That really was Q over 4 pi epsilon naught R.
But then how can you add with the denominator?
Well, how do you add any fractions with a
Then you
denominator?
got 3Q.
What's that?
Then you got 3Q, so then you would...
Well, I mean, really, if I have 2/3 and I have 1/4, what do I have to do? Always. Common denominator, right? So look at the denominator here. Look at the denominator here. They have the pi epsilon naught R in common. The difference is this is 4 and that's 8. So what do I have to do to this?
Multiply by 2.
Right, and I multiply by 2 over 2.
Yeah.
Right?
So you add when you get 4, not 3.
Or what's 2 plus 1?
No, wait a second. She's not saying, okay. So here's one thing I'm adding, right?
Yeah.
And I'm adding this to it.
Oh, so got it.
She was adding this to itself.
Oh.
Okay?
See, I wasn't that crazy.
All right. This is hard stuff, guys. Don't beat yourselves up. You gotta remember, this is stuff that people in college, their third year in college, that have had lots more calculus than you guys. Some of you have not had any calculus, so don't beat yourselves up. Okay, now we're moving on to the next one. Is that still working back there?
Yeah, it's still going.
Still scribbling.
Well, that's right, we have a short day today. What are we at here? Well, I got time to do a little bit. I have time to do a little bit more. So what do you think? How are you doing?
Much better now.
Okay, so can you start to try some tonight, maybe on your own?
Yeah.
Okay, let me tell you already, since I know we're going to be cut short of time here. These over here in black or gray, you could try them, but it's going to turn out that it doesn't make sense because you're going to get natural log. And the reason why that doesn't make sense, what's a natural log at infinity?
I don't know.
Yeah, right, it's infinity, it's some kind of weird thing. So you can still do this, but it won't make sense. Some of the answers for the potential. You can still do the E field, absolutely.
Yeah, can we have a quick rundown of what our suggestions are?
Oh, yeah. Yep, good point, thank you. On the front side, we're getting ready to do a charge that's inside of a conductor. Okay, on page 2, you can either look at that as a very thin conductor, or you can think of it as a sheet of charge that's been bent around into a cylinder. It's the same thing, same idea. The second one down, that would be an insulator. You can see how the charges are uniform. That's solid, insulator. It's distributed uniformly throughout. The next one down that's gray, I try to use gray for conductors. That is a conductor, a solid conductor. The very last one on that page is a pair of nested conductors. The inner conductor has a charge Q1. The outer conductor has a charge Q2. And I'm going to do it in class as though Q2 equals negative Q1.
In other words, they're going to be equal and opposite. Okay, then the last page, the top one is notice it has a non-zero thickness. That's a conductor. The next one has two conductors really near one another. It's really hard to see that, but on the bottom one is positive charges, and the top one is negative charges. That is a capacitor, by the way. And then the very bottom one, that's just a thin sheet it's an infinite sheet of charge. You could think of it as a conductor if you want to, but it's an infinite sheet of charge. And that would be an infinitely thin conductor.
Okay, I do have a little bit of time, I think.